right, so let's get into it. The problem. So for a long time, physicists have been ignoring a problem, which is the incompatibility of special relativity and general relativity with quantum mechanics. And both of these theories are heavily experimentally verified, which means they produce theories and they produce data which can be verified with what we see in real life and what we can collect through experiments. So both of these are heavily experimentally verified, but they differ in two main ways. And a little background between relativity and quantum mechanics. Relativity usually applies to the larger scale, which is large masses and large speeds, and quantum mechanics is more the small scale. So where they overlap is where they're incompatible and inconsistent. And the first difference is what I like to call the zoom, and that is that Einstein's theories of relativity rely on the smooth curvature of space-time to describe gravity's effect. So the math involved with calculating gravity and the effect of gravity relies on smooth curvature and calculus and calculating curves and areas under the curve and stuff like that, which means that each time you zoom in and every time you zoom in closer to something, closer to an object in space, the space-time remains flat and remains very smooth, which is not consistent with what quantum mechanics says. And what quantum mechanics says is that once you zoom in a certain distance, fluctuations and uncertainty occur. And as you can see here with my squiggly lines, energies change really quickly and particles borrow energy from space-time and create to antiparticles and explode and create new ones all the time as you zoom in further and further. So that kind of uncertainty and fluctuations makes it so that space-time isn't really smooth, but it changes and it's radically different at small distances, which makes the math behind general relativity basically break down, and it makes it so it doesn't work. The second inconsistency is what I like to call a good old-fashioned race, and that is that Einstein and his theories were vehemently against the theory that something could move faster than the speed of light. He thought that was the limit. That was how fast anything could go. And in fact, his unification of space-time theorized that velocity was shared between the space dimensions and the time dimensions, and if energy was all diverted into space dimensions, that time would not pass. That was one of his theories. And you can kind of see it in my little vector drawing, and similar to a velocity vector or something to that nature. If energy is shared, if there's both time energy and space energy, velocity is not equal to c, it's not equal to the speed of light. But if time goes to zero, your total velocity is equal to velocity in the space dimension, and v equals c in that instance. And in quantum mechanics, Bell's theorem, which I found on YouTube, and you can look that up, I link it later, is consistent with quantum mechanics and says that some things can move faster than the speed of light. And a little background on Bell's theorem is that it states that by analyzing probability, one can tell that quantum entangled particles do not predetermine decisions when they're measured, which implies that they do communicate at the speed of light. And the experiment uses two spin detectors, each consisting of 3 directions, so 2 separate detectors in 3 directions in the little picture that I have, up to the side a little bit, to the other side. I think they're all separated by 60 degrees exactly, but I'm not 100% sure about that. And the detectors are separated, and so in 2 different locations, and the directions of measurement are chosen instantaneous at the time of the experiment and independent of the choice of the other. So each chooses a direction to measure a entangled particle in, and those directions are sometimes the same and sometimes different, depending. It's a completely random choice and independent of the other. And the detectors either measure spin up or spin down, and the results are analyzed by scientists. And if you don't believe me, I understand that. And I found this theorem on YouTube. And the YouTube channel is Looking Glass Universe. It's very interesting. And the two videos I watched were Is Quantum Mechanics True? And Proof of Bell's Theorem. So if you want to look at that, I recommend. So, what can we conclude from this? Basically, we have two pretty incompatible theories, both experimentally verified and both backed by incredible minds. And here I have Einstein and Bohr, which are two prominent scientists on either side, Einstein being relativity and Bohr being quantum mechanics, and they're having a little discussion. And the discussion is, Einstein says, "So it appears we have a problem," and Bohr says, "Yep, how do we fix it?" Well, physicists can continue to avoid the conflict and only focus on one theory or another at one time, which is what they've been doing for most situations. But people have a luxury that physics does not: ignorance. Physics ignores nothing. So what that means is that we can look at one theory or another at one time, but we're living in this world and nothing has gone crazy and nothing happens between really big and really small that makes things go crazy. So I've got to assume that one set of all-encompassing rules governs all that exists in the universe. Maybe that's just me, but that makes sense. We have a universe that is consistent, so we must have laws that are consistent. And one candidate for a theory of everything governing all I've said before is string theory, and that is what I've done my independent study on. And the basics of string theory are that all fundamental particles, quarks, electrons, gluons, etc., everything in the Standard Model, consists of tiny Planck-length filaments whose properties are determined by how they vibrate in and around our dimensions. And to me, that sounds perfectly logical. Sure, maybe if you go further into an electron, they're made up of similar things as a gluon and as everything else, as a quark. But the thing that a lot of people have to wrap their heads around is that in order for string theory and all the math behind string theory to cancel out, all good and perfect, we need to have 11 dimensions, which is very interesting because we see in 3 dimensions, 3 space and 1 time. That's what we're used to. That's what we see in. We can't really picture anything else. And in string theory, we have 3 extended dimensions, which are what we see, and 1 temporal, time, and 7 curled up dimensions microscopically in the fabric of the universe. All right, and these 7 hidden dimensions are thought to reside in Calabi-Yau shapes that resemble this drawing that I have on the left. And please keep in mind, this is only a 2D rendering of a 7-dimensional object, which we can't really picture in our minds because we're used to 3D. So it's a 2D rendering of a 7-dimensional object in 3D space. So please keep that in mind when you're looking at my little drawing. And I'm no artist, so... And strings either loop around sections of the Calabi-Yau shapes, or they sit in little nooks and crannies of the shapes, which are, and depending on whether or not they loop or they sit in, radically affects their mathematical properties and what they can do for the theory. So that's something to keep in mind. All right, and some pros about string theory is that it sheds new light upon problems like the ones I mentioned before between relativity and quantum mechanics. And one example of that is, unlike typical point particle theories, which relativity and quantum mechanics are, those theories allow for infinite zooming. And one way to picture that is that if you're in Desmos and you have a grid and you have a point and you're zooming into that point, you can see the grid getting smaller and smaller and technically getting bigger as you're zooming further into it. But the point stays the same size no matter how much you zoom in or out. And that's the point particle theories. They have 0-dimensional points, but in string theory, the math sets a limit to how much you can zoom in, and that limit is the Planck length, which is 10 to the negative 33 centimeters. So pretty small. And the theory says that after that, no more zooming is allowed. And this keeps the math of Einstein's theories of relativities, in which complete smooth Riemann curvature is needed to calculate theorems and to calculate data. This keeps that at bay. And it also alters what we think of as the Big Bang theory, which is pretty much agreed upon as how the universe started. And the Big Bang theory states that all of our matter, mass, radiation, space, and time compress into a single, infinitely small point with infinite energy. And if you don't hear the mathematical alarms blaring, get your ears checked, honey. It's a little joke that I wrote because in particle physics and in theoretical physics, one huge red flag to the fact that you're doing something wrong is getting infinite values for energy or for space or time. Getting infinities is you're doing something wrong. So the string theory suggests that whole nonsense instead is crushed into a sphere with the Planck length as the radius, and which is a little bit easier to swallow, kinda, because it's still a really small really small circle, and it's kind of hard to imagine anything being compacted into that area, but it's a little bit easier to picture instead of an infinitely small area. And also, through rigorous mathematics, it has been theorized in a universe consistent with string theory that tearing of the fabric of space-time is not only allowed, but happens very frequently. So that's another thing that's a little different in string theory. All right, now some things to keep in mind. So string theory is not an experimentally confirmed theory, which is where a large amount, if not all, credibility from the scientific community stems from. So it should definitely be taken with a substantial grain of salt. And most opposition to string theory falls into one of two categories that I have listed. The first being a quote from Watt, who is known in the field of string theory as being an opposer to the theory. And he says that string theory is not even wrong. That's actually a title of one of his books. But how I interpret that is that many take issue with the untestability of the theory, saying it doesn't hold up to the scientific criteria of a good theory or law. Meaning that a lot of classic physicists and scientists believe that something's only correct if you hypothesize and then test over and over again and have so much evidence that you really can't refute it. So it doesn't play along to that traditional mindset of science, so a lot of people are opposed to that. And one thing I have is this little guy, and he says, "Hey, I think the universe is governed by a purple monster." And under that I have, just because you say it and you can't prove it's wrong doesn't mean it's right. So that's a easier way to see that criticism with a different situation. And the second line of logic that opposition to string theory falls into is that some think that string theorists are determined to be right and will twist and contort their findings to match the hypothesis somehow. And a quote that I have from the book I read for my independent study, which is The Elegant Universe. The author of that said, "When you know the answer you want, it's often too easy to figure out a way of getting it." And how I kind of interpret that is that string theory is so broad and so, because it's the theory of everything, that's the coined term for it, it's so universal that you can take any sort of finding that you might get and make it make sense in the theory. So a lot of opposition to string theory says that there's no point to it because it's so vague. But my takeaway to the whole thing is that in all my research, string theory might be right and it might not be right. But scientific advancement is scientific advancement. And if string theory is wrong, it will lead us to something that isn't, guaranteed. And I just want to say thank you, Loss. This has been a lot of fun and really expanded my mind to a branch of science that I never really knew existed and that I have found super, super interesting. So thank you for giving me this opportunity. Thanks. Bye. Have a great summer.